Attention. It's the core innovation behind all modern language models. But how does it actually work? Let's say we have a sentence, the dog was. This consists of 3 tokens, each of which maps to a vector representing its meaning, referred to as its embedding. The embedding of dog contains the meaning of dog. These embeddings are fed to a neural network, which predicts the most likely next token. Here it outputs barking. But what if we had the tokens, the hot dog was? The embedding of dog is the same as before, and the embedding of hot encodes the meaning of hot. If we combine these, the model may naturally predict something like panting. But this isn't the right most likely interpretation of hot dog. We need the meaning of dog to change, when in the context of hot dog, this is where attention comes in. But before we continue, let's recap the dot product. We have 2 vectors A and B, and we want to measure how similar they are. To do so, we use the dot product. First, we multiply the corresponding components, then we add up the result. This is the dot product, which can also be written like this. As dimensions get larger, this can grow to extreme values. So we divide by the square root of our dimensionality to keep the values manageable. Now back to attention. We have our input tokens, the hot dog was, and their embedding vectors. We then project dog to a vector called Q, referred to as the query vector. This vector asks, what am I looking for? We then project hot to a vector called K, referred to as the key vector. This vector says, here's what I provide. If we take the dot product of Q and K, we get the attention score. That is, the amount that dog attends to hot. We do this for every key, which gives us all of our attention scores. Here are some example values, where dog may attend most to itself, but then also to hot since it's relevant to its meaning. We then scale these values by their dimensionality, like earlier, and then finally we apply softmax, so they all add up to 1. These are now our attention weights for dog. That is, how much dog should attend to every other token. But we still need to incorporate the meaning of those tokens. To do this, we project one more vector from every token, called V, referred to as the value vector. This vector says, here's what I offer. It provides the actual meaning of the content to share. If we multiply these by our attention weights, we get a weighted sum of the meaning provided by every token. That is, the final in-context meaning of dog. We do the same for every token, so every token attends to every other token. That's attention. If you want to walk through this at your own pace, we also made an interactive written version. And if you'd like to be notified of future interactive write-ups like this, sign up for our newsletter.